Hello student to the course of physics of linear and nonlinear optical waveguides. So today we have lecture number 38 and we will going to continue the calculation related to the coupled mode theory. So in the last class we figure out the differential equation of two amplitudes of these two modes which are going to evolve over the system in this way. This was one equation and another equation was this. So today we are going to solve this equation, decouple this equation because this is a coupled differential equation and we are going to solve this, and after putting some boundary condition try to find out what is the explicit form of A and B. Well, let us make a derivative. So in order to decouple that, let us make a derivative of the first equation with respect to z, so that I can have this. I simply make a derivative of the first equation and I am having this. This is a standard way to decouple this kind of equations. Now after making the derivative, I have this term in my hand. So I can replace this term here, and also I have a b here which I can replace from the first equation itself because b is here. So I have this term here, I can replace from this, and I can also have, let me define in a different, I also have a b which is sitting here. So I am going to replace this, so entire equation will come into the form of A. So if I do then it should be I kappa 1 2, then this term will be I kappa 2 1, and you can see it is A multiplied by e to the power of minus of I delta beta tilde z. So this term and this term will going to cancel up, and another term will be simply 1 plus I delta beta tilde b. I am going to replace as 1 divided by I kappa 1 2, and then dA dz, because I just replaced my b from here. So it should be dA dz divided by 1 by kappa 1 2, and then it should be 1 delta beta with a negative sign. So this again will going to cancel out with this one. So I have this thing. So eventually I have d2a dz square minus I delta beta tilde dA dz plus I say kappa square A equal to 0. Here this kappa square I write it as kappa 1 2 multiplied by kappa 2 1, and this kappa is called as kappa as a name which is called the coupling constant. So I can have a general solution for that, and for this kind of differential equation we know how to calculate the general solution. So I can assume a general solution of the form say C1 e to the power of m1 z plus C2 e to the power of m2 z, and then I put this solution here to execute the value of m, and m12 can be, if I put this there in the equation. Okay, let me do this step one by one. So, I put this here, and after putting that I can have m square plus I, it should be minus I delta beta tilde m plus kappa square equal to 0. So, I can have my m 1 2 as minus b. So, the solution of this quadratic equation is this minus of delta beta square minus 4 of kappa square, straightforward calculation 2, which I can write as I delta beta divided by 2, then plus minus of I one other term gamma, because there is a negative sign. So, it should be come out as where gamma I can write as kappa square plus delta beta tilde divided by 2 square of that and whole to the power half. So, this is my gamma. So, my Az will be simply e to the power of I delta beta tilde divided by 2 z, and then C1 e to the power of I gamma z plus C2 e to the power of minus I gamma z. So, I have the solution for Az in this form. Mind it, C1 and C2 are the solutions, and we need to evaluate this solution putting the boundary condition. So, B I can also figure out. So, Bz we know in terms of A, and which is minus of I kappa 1 2, then dA dz e to the power of minus I delta beta tilde z. So, this is the B in terms of A, and that I can find from this equation, this first equation. So, now I know what is the value of Az, because I already solve the differential equation. So, I can extract the B out of that. So, in order to do, I need to calculate dA dz. So, dA dz will be I delta beta tilde divided by 2 e to the power of I delta beta tilde z by 2, the derivative of the first term multiplied by the second term e to the power of I whatever we have gamma z plus C2 e to the power of minus I gamma z plus derivative of the second term e to the power of I delta beta tilde z divided by 2, and then I gamma C1 e to the power of I and then minus C2 e to the power of I gamma z. So, I have this expression for del A del z, which I can write as I e to the power of I delta beta tilde z divided by 2, and then if I take say C1 common, then it should be delta beta tilde by 2 plus gamma. I take C1 common from this 2 and then e to the power of I gamma z will be here and plus C2 delta beta tilde by 2 minus gamma, and I should have e to the power of minus I gamma 2. So, here I have a minus sign, sorry, this one. So, dA dz I calculate. So, I can calculate my B, and my B will be simply 1 divided by kappa 1 2, then C1 delta beta tilde divided by 2 plus gamma. This calculation is little bit lengthy, but straightforward. I suggest all the students to please go through the calculation at least once, and then you can realize that how one can extract all the information out of starting from these Maxwell's equations, Maxwell's wave equations. Z and then multiplied by the first term z by 2. So, I just extract dA dz from the solution A that I figure out here, and then I put this value here, and when I put this value I have the value of B here. So, I finally I find my B, and let me write it once again what A value I calculated. So, my AZ was e to the power of I delta beta tilde z by 2 multiplied by C1 e to the power of I gamma z plus C2 e to the power of minus I gamma z. That was the value of A I figure out. So, now I know what is my A, what is my B, and C1, C2 are the constant that we will going to evaluate with the boundary condition. So, that is important. So, boundary condition I already mentioned earlier, that this is the structure of the waveguide, say, and this is waveguide 1. So, at waveguide 1 I launch a light here. So, this is waveguide 1 and this is waveguide 2, and this along this direction I am having my z. The refractive index profile, if I draw, it should be something like this. So, this is the refractive index profile that two waveguides placed side by side. So, the boundary conditions suggest that simply this is at z equal to 0. So, the boundary condition simply suggests that A at 0 is some value A 0 and B at z equal to 0 is simply 0, because there is no B at all at waveguide 2. So, with these two boundary conditions we can evaluate the constants. So, let us try to find out the constants. So, A 0, which is A 0, should be equal to C1 plus C2, because A, if you look carefully, if I put z equal to 0, z equal to 0, it should be C1 plus C2, and here z equal to 0 1. So, simply C1 plus C2 is A 0, and for B, B 0, which is equal to 0, is equal to delta beta tilde divided by 2 C1 plus C2 plus gamma C1 minus C2, because here if you look carefully, if I put this equal to 0 and this equal to 0, then this is 1 and this is 1. So, it should be something like delta beta, and this 1 by kappa 0 is in the denominator. So, this term will go to 0. So, it should be C1 and C2, C1 plus C2 delta beta by 2 and the rest term plus gamma C1 minus C2, these things will be 0. So, I can have gamma C1 plus C2 as A0 gamma and gamma C1 minus C2 as delta beta tilde divided by 2 A0, and if I do that calculation, I can find that gamma C1 is equal to half of, if I just add half of gamma plus delta beta tilde divided by 2 then A0. So, that C1 is equal to A0 divided by 2 then gamma plus delta beta tilde divided by 2 C1, okay, this gamma will going to cancel out. So, it should be 1, it should be simply 1 plus gamma should be here, and C2 is A0 minus C1, which is simply A0 divided by 2 1 minus delta beta tilde divided by 2 of gamma. So, I have C1 and C2 in terms of A0, which is my boundary condition, the initial amplitude, and delta beta 0 and gamma. Now, the important thing is the power, because that I eventually going to measure. So, the power is related to the mod of Az square. The amplitude square is directly related to power. Ignoring the proportionality constant, it will be simply, if I write, it will be simply C1 e to the power I gamma z plus C2 e to the power of minus I gamma z, and then C1 e to the power of minus I complex conjugate of these things plus C2 e to the power of I gamma z. Note that C1 and C2 both are real, so that is why I should not put any kind of star over here. Well, these things can be written as C1 square plus C2 square plus 2 C1 C2 cos of 2 gamma z. If I multiply, you will going to get this one. Well, C1 square plus C2 square, I can also extract the value, and this value will be simply this one, 4 gamma square. I just have my C1 square, I have my C2 square. If I make a square and add, then I will going to get this one. And C1 and C2 also I can calculate. It should be A0 square to the power A0 square divided by 4, and then A plus B into A minus B. So, A minus delta beta by 4 gamma square. So, my Pz, which is P1z, which is the power associated to waveguide 1, is simply A0 square divided by 2 1 plus delta beta tilde divided by 4 gamma square, then plus A square divided by 4 multiplied by, because it is a 2 term associated with this 2 C1 C2. So, this delta beta tilde square divided by 4 gamma square and then cos of 2 gamma z. So, this thing I can simplify as A square divided by 2 common 1 say plus cos of 2 gamma z plus another term is A square divided by 2, then delta beta tilde square divided by 4 of gamma square 1 minus, because if I write it 1 minus cos of 2 gamma z. So, this I can write as say A0 square then cos A square gamma z plus simple trigonometric identity four gamma square, then it should be sine square gamma z. So, this is my P1z, it will vary in this way. Well, I can also write this in the form of sine. So, it should be A0 square plus cos square is 1 minus sine square. So, I will write cos square to 1 minus sine square. So, then I have A0 square delta beta A0 square, and then I have a sine square from this side and sine square from the first term. So, it should be sine square gamma z into delta beta tilde divided by 4 gamma square minus 1, that is one term. Now, I need to put the value of gamma. So, we defined gamma earlier. So, we have say gamma square equal to kappa square plus delta beta tilde square divided by 4. So, I can write say kappa square divided by gamma square is how much? It should be 1 minus delta beta square divided by 4 of say gamma square. I can have this. So, I can use this value here, and eventually my power will be something like A0 square into 1 minus kappa square by gamma square, then sine square gamma z. So, this is very interesting, and also when z equal to 0 I have, so P1 at z equal to 0, which I can say my P0, that is initial power, it should be simply A0 square. So, I can write this ratio as P1 z divided by initial power P0, which is at P1 at z equal to 0. So, P0 is P1 at z equal to 0 simply. It is 1 minus kappa square divided by gamma square sine square gamma z. Very important equation I have, very important equation I have. Now, after doing all this lengthy calculation, I now conclude, now I have a very meaningful equation that clearly suggests that if z increases, then this term will going to vary sinusoidally. So, this term will going to vary sinusoidally. That means, if I have a waveguide like this, so let me draw this waveguide first. So, this is the waveguide I am having. So, this is waveguide 1, waveguide 1 and this is waveguide 2. I launch a field here at waveguide 1 at z equal to 0. This is my z equal to 0. This is 1 and this is 2. This is the waveguide structure. After certain distance, there is a possibility that this field will come here, because my power will going to change sinusoidally. So, at certain length z equal to say L c, the power will come here. So, this is basically the switching we are talking about. Well, I can write a general equation if there is no loss. So, without a loss term, the total power remain conserved. The total power, I can write it is as Pt is the total power. It will be the sum of the power distributed in two waveguides, and since I launch a power in waveguide 1 which is P0, so it should be equal to P0. Hence, I have a equation P1 z divided by P0 plus P2 z divided by P0 will be equal to simply 1. P1 z divided by P0 I already evaluated, and this value what I evaluated is this one. So, this equation I already evaluated. So, from that I can also calculate P2 by P0. So, I can write P2 divided by P2 function of z divided by P0 is simply kappa square divided by gamma square sine square gamma z. So, now I have two equations in my hand. This equation suggests that how the power will going to exchange from one waveguide to another waveguide, and we find that this power will going to exchange in a sinusoidal fashion. So, let me write down the two equations side by side once again. So, this is one and another equation is this. In most of the books you will find these two equations without much derivation, but in this particular course I want to calculate all the entire couple mode theory in detail, so that you understand that how this equation basically arrived, how someone can arrive in this equation, and this is the way you can find these two equations. So, in the next class we will try to understand more about this equation, we try to solve this we try to plot these two equations, and then we will see that how the energy will going to transfer periodically from one waveguide to another waveguide. But anyway, in today's class already you understand that since this power variation is related to a sine function, there will be a sinusoidal variation of the power from one waveguide to another waveguide. So, in the switching problem we are eventually doing the same thing. So, I am just finally drawing what the problem we started with, that I had these 4 ports, and this is 1, say 2, 3 and 4. So, I launch a power here in port 1 and I find the power is coming to this one. So, this is basically a switching problem, and this switching problem can readily be understood with these two equations, and in these two equations suggest that if we have two waveguide which is placed very close to each other and behave like a coupler, then the energy can couple from waveguide one waveguide to another waveguide, and there is a periodic transfer from the energy from one waveguide to another waveguide. So, if you cut my coupler in such a way that this energy is completely transferred to here, then I can use this as a switch, optical switch. So, with this note I would like to conclude. In the next class we start with this equation and try to understand more about the principle of optical switch, and then principle of 3 dB coupler and WDM systems. So, with this note, thank you for your attention. See you in the next class.